Hello everyone. As you know, my name is Jorge. Welcome to my presentation. Actually, today is my first time presenting to an open forum, so I'm really excited. Let's see how it goes. Today we're going to be talking about my experience when developing networktime. Networktime is a Kotlin Multiplatform 2.0 library implementing the client side of a protocol for synchronizing clocks over network communications. The library is completely open source and the source can be found on GitHub, as shown behind me. Also, dependencies can be declared via Gradle, Maven, or SwiftPM, depending on your stack, of course. Now, first things first, I am Jorge. I write a lot of code for fun and at work, of course, as well. I am from and currently live in Spain, although I have lived in Sweden throughout most of my career and higher education. I have a bit over 11 years of professional experience with Android, not only on mobile, but also on automotive, operating system, and tooling development. And I currently work at Tidal, mostly with media streaming and playback logic on the Android stack. On the side, I have developed a number of projects of my own, as well as contributed to tools which you might have heard of, such as Android X Media 3 Exoplayer, Moshi, or Assisted Inject before it became a part of Dagger. I also enjoy myself some reverse engineering from time to time, and for more info you can find my profile on LinkedIn. Now we're ready to begin. The first thing we're going to do is to talk about the project. Networktime is an NTP client, so we need to learn a little bit about NTP before we can understand how Kotlin Multiplatform applies. Then we will go through the architecture of the project so we can understand how a Kotlin Multiplatform codebase is structured and how some of its internals work. We will also visit the build configuration of the different modules that make up the project. And finally, we'll make a stop at the delivery procedure for the library, as it has been one of the biggest headaches of the project, if not the biggest one altogether, really. So, time. Time is a complex topic. We all know that it represents a combination of two things: how Earth rotates relative to its own axis and how it does so around the Sun. The latter in particular takes approximately 365 days, which we simplify down to a bonus day in February every 4 years. Is that good enough? Well, not really. The reality is way more complicated. For example, neither Earth nor the Sun are perfect spheres, nor is space completely void. These and other factors mean that if you have worked with time-related software development in the past, you may have heard of sentences such as "not all minutes last 60 seconds" or "not all seconds are equally long." Certainly nothing to worry about when it comes to being on time for your next meeting, but annoying to say the least when writing code. But that's not all. Computer systems nowadays, especially mobile ones, feature clocks that are usually based on quartz crystals, which can vary in quality from system to system. Furthermore, said crystals degrade over time, yet another factor that affects the accuracy of the time measurement capabilities of a device. But even ignoring everything we have said so far, the worst circumstance is that it's not uncommon for systems to allow for users to freely set their time. And even if they don't allow it, unintended workarounds like privileged access solutions such as SuperSU or Magisk are constantly popping up, so you can never be truly certain about what a device has to say regarding time. This is absolutely terrible for any software that is time critical, but on first thought one could say that it's not too common to have time critical general user software, and I could more or less agree with that statement as a user, but as a developer I know that's a lie because there's something that every single software development company loves: analytics. So in the end, yes, having time be something not only complex but also unreliable is a huge issue for software development. In comes NTP to the rescue. NTP, which stands for Network Time Protocol, is a protocol that allows synchronization of clocks over networks with accountancy for network latency and similar factors. The basic idea is that a limited number of servers around the world are considered reference clocks and constitute what's called stratum zero of a multi-tier system where communication works both vertically and horizontally. As we go down in layers, systems give up some accuracy with respect to higher layers in exchange for query availability, down to layer 15. Regular user systems, such as personal computers and mobile devices, are typically found in stratum 3. And the node declaring layer 16 or below is the formal way to state that it's not synchronized. Oh, sorry. SNTP, as in Simple Network Time Protocol, is a specification of NTP meant to allow for simpler implementations that do not require all of the functionalities and extreme accuracy supported by the complete protocol. Network time is an implementation of an SNTP client. Narrowing things down to what we need to know for today so we can finally get to talk about Kotlin Multiplatform, Stratum 3 NTP involves periodic synchronizations, which include a number of steps. Of particular relevance to us are two. First, manually resolving the addresses of the time servers configured by the consumer, such as time.google.com or time.apple.com. This type of resolution is usually built into the network APIs that we normally work with, but this approach is not sufficient for NTP, and there's no Kotlin Multiplatform implementation of it as far as I'm aware. And then also performing a UDP exchange. This is absolutely critical to NTP, and yet again, there is no Kotlin Multiplatform implementation of UDP sockets that I could find. We will later elaborate a bit on the experience of implementing these points, but for now at least bear in mind that the project consists of both cross-platform and platform-specific code. Moving on to the architecture of the project, the repository features 6 different Gradle modules, plus a 7th one as an Xcode project. First off, we have build logic, which is a special Gradle module dedicated to encapsulating build code for reuse across different Gradle modules. In this repository, this module manages settings such as some publishing configuration or defining compilation targets, and is omitted from the picture for clarity as it offers nothing special when it comes to Kotlin Multiplatform. Then we have networktime, the core module of the tool, using mostly Kotlin Multiplatform, but also JVM and native code for the platform-specific implementations that we just talked about in the previous slide. We have networktime singletons, also using Kotlin Multiplatform, which is an optional extension to the core API that allows micromanaging clock instances. As an aside, both networktime and networktime singletons declare JVM, Apple, and Android targets. JVM and Apple targets were my goal initially, and the Android artifact is built from the JVM sources and exists by itself simply to add a manifest that declares internet permission and minimum SDK. Other native targets were possible, but I simply chose to avoid them due to this being my first adventure into both NTP and Kotlin Multiplatform. Finally, we have 4 modules that make the sample apps, one for each platform as an entry point that bridges it to the multi-platform code in the share module, which actually contains the meat of the sample app. We will soon move on to take a quick tour of the build logic of most of the modules, but before we do that, there is something I want to highlight about the sample apps. Note how I have defined different platform-specific modules to enable using tooling that is native to each platform, even though this is a Kotlin Multiplatform project. This is intended. Gradle doesn't really support building an Xcode project, and to build an Android app, it requires the Android plugin, which you could probably make work in a module that builds a Java target too, but I figured it would be simpler to have them isolated and haven't regretted it so far. So let's now go ahead for a deeper look at the build scripts of each module. The first module we're going to be looking at is networktime singletons. First, it uses an extension defining build logic to configure some details. Then it features a single source set, which is common to all of the targets, common main. As you can imagine, this name is related to how Kotlin Multiplatform manages platform-specific code and external dependencies, but also dependencies across source sets and source set grouping. Since this module features no platform-specific code, this source set is enough. We can also see that on top of adding the core library, for obvious reasons, we have also declared a dependency on a Kotlin Multiplatform library called Atomic Foo. Atomic Foo, fortunately, supports all of the targets that network singletons does. So this is all we need to do. But let's now move on to something a little more complex. The module we're going to look at now is the one shared by all sample apps. On a first glance, we see the block which configures the targets the app can be run on and some other small details. This is close to what the build logic extension we just mentioned does for library modules, but with a few particularities that warrant not reusing said extension here. Just as in the network singletons time case, this time we only see one source set in the build script with a number of Kotlin Multiplatform dependencies as well. But if we go to the source, we can see that we have source that's iOS specific. Why is this necessary and why are we doing it? Well, we need it because, even though as we said before, we have modules for each stack that we want to build for. Replicating the design of the other sample projects would mean that the entry code would need to refer to compose multi-platform from an Xcode project, which is not directly possible. So what we do for the iOS case in particular, is not needed for the other cases, is to define an intermediate API, which here I'm calling main view controller, which sits just above the compose multi-platform code. Then we build the share module in a way in which it can be consumed from an Xcode project, meaning that then our iOS sample app Xcode project can call the API defined in main view controller and thus reuse the common code in the share module, even though the sample Android and JVM projects do so without the need for an intermediate facade. Here is the entry point module for the Android app, which configures some trivialities and some Android-specific dependencies for the glue code to the share module. Similarly, the JVM entry point module is very simple additions on top of JVM-specific dependencies for the glue code. Then we have the PBS Pros file for the iOS sample app module, which is a bit of a meme if you don't have Xcode in front. And we now get to the module involving the richest configuration, the main library module. First off, if we take a look at the source sets, we can now identify the new JVM main for JVM specific code, obviously. Then there is Apple main at the top, which, as you can probably guess, groups all supported Apple platforms declared as targets. And like it was the case with the sample app module, networktime and networktime singletons support both iOS and non-iOS Apple targets. So using iOS main here would not have been enough. Finally, almost at the bottom, we can see a new, different-looking type of source set called native interrupt. This source set includes code to be consumed by Kotlin Native's C interrupt tool. This tool allows interacting with native APIs from Kotlin by generating Kotlin bindings from file that performs native calls. This allows interacting with native APIs from Kotlin by generating Kotlin binding. It is somewhat equivalent to using the Java native interface or bridging headers in Swift. In this case, networktime defines the same C interrupts configuration for all Kotlin native targets it supports, which for us, fortunately, is only Apple ones. We will later see why. Finally, we have the continuous integration and delivery setup. We're not going to talk much about CI, as it's just a regular build, static analysis, and dependency report generation pipeline with nothing really particular to Kotlin Multiplatform. You've probably seen plenty of these over the years. But the continuous delivery setup is a little particular. It works in the following way. First, when I want to make a release, I tag a commit which must be on main using a tag name that follows a specific pattern. And that pattern is the version and then a designated suffix. This triggers a check to make sure that the tag is indeed on main, and then a very special job which generates Xcode frameworks for all targeted Xcode versions and moves them to paths specified in the package.swift file, which is a file somewhat similar to a POM file, but that sits on the repository itself. Then these frameworks are committed, so they can be downloaded when the package is referred to from an Xcode project, or manually if desired, of course. And finally, a new tag is created pointing to this commit. This tag drops the suffix I mentioned earlier, and thus becomes the desired version and has all the binaries for Xcode projects in the repository, which obviously is not ideal. The reason for this is that in Apple's Swift PM ecosystem, you're supposed to download dependencies as source whenever possible so that they are compiled locally. But if you do this with a Kotlin Multiplatform project, people won't be able to compile it because they won't have the Kotlin Multiplatform stack. So we have to work around that limitation. Finally, the procedure ends by dispatching one final job on the newly created tag, which creates a GitHub release from it and publishes the JVM and Kotlin Multiplatform Maven publications to Central. There are other approaches, obviously, especially for the Apple part, which I've gone back and forth on for a fair amount. Let's see what some of these are. The simplest alternative I considered was to drop the double tag procedure. Instead, I would push a tag I want to have CI build the Apple targets and commit them, just as we saw before, but instead of creating a new tag on that commit, recreating the tag I initially pushed, but pointing to this new commit. It would have been a cleaner approach when you look at the history, since you would only have one tag, and it had a bonus advantage in that there is a Gradle plugin called KMM Bridge that helps automating this for you. But the approach had two cons, which made me opt out of it. First off, you need to force push to move the tag. I really do not like force pushing references that are shared, such as your usual main or develop branches, or in this case tags. And most importantly, the thing I was the most annoyed with in the chosen procedure wasn't having two tags per release, but committing binaries. This alternative didn't really do anything about this problem, so I gave it some consideration just in case, but never stood a real chance. To solve the problem of committing binaries, the first solution that came to mind was to do so on a branch other than main. The idea was that CD would branch out of the commit that I tag as dispatch for that version, and then commit the Xcode frameworks on that branch, with that commit being the one to receive the final tag. If you think about it, this very much resembles a standard delivery procedure for an application. You branch off of your work at a certain point where you start a release candidate branch, and eventually you make a release from what you have in your release candidate branch. Now, obviously, this still means I have to keep the binaries in the repository, so it doesn't solve the problem, strictly speaking, but it gets the binaries away from the regular development workspace, which is something. However, I still was not convinced. It is important for me that when I look at the Git history of a tool repository, the release tags are present at a glance. And with this procedure, release tags were kind of hidden away from my main branch, making this goal difficult to accomplish unless you know specifically how dispatch tags act in the procedure. And I don't want people to have to know the details of how CD works, so I ended up ditching this option, which takes us to the final option I considered. This is very simple to explain. Instead of hosting the binaries on the repository, which I already explained that I do not want to do, and having to add this extra layer of complexity of the double tag, I will just host the Xcode frameworks elsewhere. This makes for a much simpler CD infrastructure due to the uniform characteristic of the setup. The only issue to solve here is where do I host the Xcode frameworks? Because normally, if this was like a JVM project, you would just push things to Maven Central, but the Xcode frameworks don't use Maven. So the solution is complicated. Basically, there's no Maven Central-like equivalent for SwiftPM Xcode frameworks. Aside from putting the binaries in the Git repository, there's two other alternatives. The first one is to host them on GitHub releases, and it looks like this works on the surface, but it's not viable in my opinion if I want the tool to be taken seriously. See, one of the things you don't know that you value a lot from Maven Central is that packages cannot be deleted, but GitHub releases can. If I was hosting a package on both Central and GitHub releases and deleted it from GitHub releases, it would still be available on Central, so nobody would care. But if I rely on GitHub releases for distribution and one day I decide to delete a GitHub release, I would cause a bit of trouble. Companies don't like this kind of risk. So yes, there are ways to mitigate those problems client-side, but they're conditional and they require you to invest time on tasks that you just don't want to be putting time onto. To delete the artifacts while I'm instead keeping them in the Git history, yes, I can still overwrite the Git history, but the detached commits are still going to be on GitHub for a while, so it gives you a little bit of more safety against the fact of me randomly choosing to burn the world away for whatever reason. Then the other option would be to just host them in some generic cloud storage solution, but in practice it has the same issues as GitHub releases, and it actually costs money, so it's probably strictly worse. So hopefully by now I have given you a good insight to help you think about how to structure some of the key aspects of a Kotlin Multiplatform library project, as well as help you understand why its delivery infrastructure can look a little wacky. Now we're going to move on to the inside of the project. Let's start by looking at some of the most positive highlights of my experience when writing Kotlin Multiplatform code. The first big win with Kotlin Multiplatform that I would like to highlight is management of business logic, which is what you see here. The platform-agnostic business logic of SMTP mostly involves bit management. Often this is a topic that can sound pretty daunting to mobile developers, as it's not usually something we have to deal with. To top it off, in order to implement the corresponding logic, I had to learn how NTP makes use of bit-level structures. Now, none of these things was a titanic, impossible task, but they were things that took time to do. However, because bit logic and NTP packet structures are domain knowledge defined outside of any particular stacks, they were trivial to write using platform-agnostic Kotlin code. Generally speaking, this is very good, because it facilitates reusing code that was set up in the past in other circumstances, especially if it was written using non-platform-specific Kotlin APIs, and also it means effectively no entry barrier to developers who already have experience with Kotlin, and a very trivial one for those who do not have it due to how high-level its syntax is. When it comes to this project in particular, this meant that no other devs had to spend any time learning about NTP or bit management with Kotlin, nor did they have to do the same when it comes to bit management in Swift. Given how product people pushing for time saving are everywhere nowadays, I consider this aspect of Kotlin Multiplatform a huge win. The next positive point we're going to talk about is Compose Multiplatform. Sorry for the flashbang, by the way. Behind me you can see screenshots of the sample apps running a JVM, an Android emulator, and an iOS simulator. They share the vast majority of the code, with each of them having just a couple of lines of target-specific code that delegates to the shared code, as we explained earlier during the presentation. This was my first experience using Compose Multiplatform, and it was surprisingly easy to set up the projects to be able to build like this, in part due to the absolutely fantastic system it has that provides built-time error messages when you use a version of Compose that is not compatible with the version of some other Kotlin tool you are using. I found the system to be very, very useful, as Kotlin Multiplatform is an environment that is still evolving quite quickly, with the version I use in my project changing multiple times throughout the development timeline, including a change as large as migrating to Kotlin 2. Now, we're going to be looking at multi-platform dependency management. Earlier on, when looking at the project structure, we saw some dependency declarations, but what is a Kotlin multi-platform dependency really? Kotlin multi-platform uses a combination of Maven and a Gradle-specific descriptor called a module file for dependency management. Instead of involving a single Maven publication and its POM file, Kotlin multi-platform projects produce a Maven publication for every platform that they declare support for, plus an umbrella publication, which is the one that consumers need to declare. Then, by using the module file, Gradle can automatically resolve which of the publications need to be consumed depending on the targets that you're trying to build, which is great because it means consumers do not need to redeclare pretty much the same dependency once for each of their targets with slightly changed coordinates every time. What you see behind me is a split of a trimmed-down version of the module file, which is a simple JSON. Finally, putting multi-platform dependencies aside, source-specific dependencies are supported too. So if you need certain dependencies only in a given source set, you can add them there instead of in common main, as we have shown in previous screenshots. This looks like normal and just the way things should be, but think about all that's going on behind the scenes. Mainly due to the different tuple targets and architectures supported, the reality of the diagram you're seeing is closer to over 30 different dependencies. It would be pretty annoying to have to manage all of those manually, so I value a lot that Kotlin Multiplatform does it for me. And we're going to close this section talking about collaboration. This is a factor which I have found to be very important throughout the development of the tool from start to finish. First and foremost, this would not have been possible without the help from an iOS developer from my team, who I bother on repeat. Even though I wrote all of the code, Apple-specific and otherwise, his recommendations when it comes to choice of stack, as well as support with Xcode and runtime environments, were invaluable, and it's always a very nice experience to collaborate with other developers. Next, I would like to mention the insights provided by a couple of members from TouchLab that I had the chance to talk to. TouchLab is a company that does some work for Block, Tidal's parent company, and provided some good discussion in the topic of CD that we talked about earlier. Shout out to them. Finally, focusing on collaboration with JetBrains, I also want to highlight that it has just been outstanding. When it comes to issues in the tracker, I reported 10 different Kotlin multi-platform issues throughout the development of my tool, and if I don't misrecall, only one didn't have a single answer from JetBrains. Otherwise, all of them have been replied to and addressed within a week, with most getting at least an initial reply within the first couple of days. I think anyone who has tried to communicate with developers of a large project without a direct partnership involved will agree that this communication dynamic is extraordinary. In fact, I think it is so good that I have serious doubts that it will stay as good going into the future if Kotlin multi-platform grows more and more popular. But hey, for now it's what it is, so that's good. Now, to be able to make a fair judgment, we also need to look at things that have been not so great. And the first one of those is going to be IDs. Even for a relatively simple project like this one, which only targets a couple of really different platforms, I have had to use 3 different IDs: Xcode to manage the iOS sample app, Android Studio for the Android one, and IntelliJ IDEA for everything else. Every IDE works a little differently, with Xcode having a larger role in project management than the others, which rely more on build system code via Gradle. You also need to manage the different runtimes, meaning at least a couple of emulators or real devices. This type of setup is not only annoying to work with, but also resource demanding, so you need a very good machine. Theoretically, JetBrains offers a Kotlin multi-platform plugin for IntelliJ, which should simplify things. It works sometimes, it doesn't really work some other times. In the end, you have to think that as a developer, if over a long period of time, day after day, you have to constantly switch between IDEs to correctly test things, what will inevitably happen is that your tests will become less complete and inaccurate, and this will affect your product overall. So this was a bit annoying. Also, once you think about less trivial scenarios, such as, for example, debugging your multi-platform code from Xcode, the situation gets even more complex. So no matter how you look at it, it's not ideal, really. Now, platform-specific code clunkiness. So Kotlin multi-platform needs to accommodate the syntax for how different runtimes work, which sometimes translates very well with constructs such as those used for memory pinning. But others, like convert or memscope, are not straightforward to understand. And bear in mind that Kotlin multi-platform is still a very young technology, so your Google skills are not going to yield as many results as they do when you research something on a well-established stack such as Android. This, alongside the fact that pretty much none of these symbols feature any documentation, make the code you're seeing behind me rather easy to read, but rather hard to write from scratch. Now, let's not fool ourselves. Kotlin Multiplatform still uses native concepts, so these constructs are required, but I won't lie. Having to learn first how to use them in the specific platform and then how they are mapped into Kotlin bindings was annoying, and it made me wonder at times if it would not just be simpler to bypass the Kotlin bindings and then just use C interrupts as much as possible. Speaking of C interrupts, we're going to talk about the network framework. I invite you, when you're bored, to check out the JetBrains issue tracker issue that I link in the slide. The network framework is the reason why networktime makes use of C interrupts, in particular for UDP sockets. This framework is available in most modern versions of Apple platforms, and it is what URL session, which is the usual suspect for HTTP operations, builds upon. Unlike domain resolution, which can be implemented in platform-specific Kotlin code, the Kotlin bindings to the network framework API have been broken ever since it was introduced. And that's not exactly like 2 weeks ago. It's 5 years ago now. They never worked. Or they haven't really been broken. To be fair to JetBrains, it's just that this API is a little special. It needs some particularities that I guess JetBrains haven't worked out yet. But in any case, whoever's responsibility it is, the reality is that the Kotlin multiplatform bindings for this API do not work, which makes it impossible to write UDP sockets using Kotlin as of right now. So what I did instead is I used C interrupts. I wrote the socket logic in C, and then I skipped the Kotlin bindings by using C interrupts. And I mean, don't misunderstand me, it's nice that Kotlin Multiplatform or Kotlin Native has something like C interrupts for when you have to deal with native code, but I want to use it when I want to, right? Not because the actually intended tool is broken. So that was a bit disappointing. The next point is going to be about how APIs look for non-Kotlin consumers. In simple cases, such as calls with trivial parameters or extension properties, things work just the way you would expect them to work. You can see an example of this at the bottom with a singleton extension. But there is a number of significant issues too. If you've worked with NTP in the past, you've probably configured a server pool such as time.google.com. However, there's a large number of other options to configure, and networktime supports some of them. But because most of them require NTP-specific knowledge and it's not really common to customize anything other than the pool, networktime uses a combination of var parameters and parameters with default values to offer a simple API to those who want it. This works great when called from Kotlin code, for example, but from Swift, as you see, none of these mechanisms work the way you would like them to yet, which becomes an impactful issue, as not only does the API become extremely verbose, but also consumers are now forced to know appropriate default values for each variable. In this case, for example, none of them should be 0, which is what this code autocompletes them to by default. This is another of those things that can be worked around by using third-party tools. Again, shout out to TouchLab on this, but in my opinion, it's the kind of thing that you'd expect to be in place already in the official stack. Now, we've put all cards on the table, so let's look at my heavily opinionated thoughts. The first topic I would like to give my opinion on is Compose Multiplatform. Is it really ready for cross-platform UI development? Well, that's a huge question, and the answer, as with most things, it depends. For cross-platform prototyping or testing UI-less tools, I think it is. That's effectively what I have done with the networktime sample apps. But for production, it gets a little trickier. In particular, if you're thinking about desktop, I would say it's probably not what you're after. It's not even for a technical reason, really. It's just, in my opinion, the different script characteristics and user interactions that they have with desktop systems may make it so that multi-platform UI development is not necessarily convenient for production systems. But for mobile, I have to start, of course, with a disclaimer that, as you have seen earlier, my UI requirements were absolutely trivial, whereas a real use case would likely involve more complex situations, such as navigation, this kind of thing. So take my opinion with a little grain of salt. But still, it was fairly easy to set up the projects, and in theory, Kotlin Multiplatform supports bidirectional integration with both Swift UI and UIKit. With this in mind, personally, I think Compose Multiplatform is not only a solid option, but probably should be the one to go to by default for a good amount of apps. At least if you're going with Kotlin Multiplatform already anyway. I think that worst case, a few Gradle changes will allow you to conserve the Android code as is, so you'll only have to rewrite the iOS UI, which leaves you at an amount of effort that's only slightly above having gone with a traditional approach. And again, for most cases, this would be like the absolutely worst scenario. And the big question, is Kotlin Multiplatform ready? Well, once again, it depends. First off, I haven't tested JavaScript targets. The reason for this is because UDP support in JavaScript is not really standardized as far as I know, and I felt like it would have been pushing complexity a little too much with all other unknowns I had at the beginning of the project. Plus, I have also not tested non-Apple native targets. Additionally, we already saw how the bindings for the Apple Network Framework literally do not work. They never have worked. Cross-platform support for coroutines we haven't talked about, but it's also not great. It can be made to work, but it doesn't just work out of the box as you would expect. You need to write some bridge code. Finally, we explained that the APIs that become exposed to non-Kotlin code are not necessarily good. So things don't look that great, do they? Well, in my opinion, it's quite the opposite, actually. No lie here. Kotlin Multiplatform will never completely replace native development, I think. I'm quite certain of it, in fact. This development would have to outpace that from companies putting more resources into the technologies and having better insight about their futures earlier. But that doesn't make it useless in most cases, and neither do most of the points that I just mentioned. First off, both you and your product owners would already be very happy if you can share code between iOS and Android, including JavaScript in that sharing is just a bonus. The bindings for the Apple API for protocol level networking being broken is mostly relevant in practice. We've seen how easy it was to bypass the bindings using C interrupts, plus how often do you do protocol level networking anyway. And you have catered to cover more common higher level networking scenarios as well as non-UDP sockets, right? So not a real issue. Then making coroutines works is as easy as using something such as suspend coroutine, completable defer, or writing a custom dispatcher. It really isn't much of an issue as long as you have a basic understanding of concurrency on each platform. And the only reason for you to care about generated API issues is, well, if you offer an API, which if you do, you can just wrap it in native code to offer a proper API where it doesn't happen automatically until the issue gets addressed. It really shouldn't be much work. So, in my opinion, there's no reason to avoid KMP in most cases. In fact, I do think that while it's important that you keep up with native development, not having Kotlin Multiplatform in your CV will probably hinder your career moving into the future a little bit. Therefore, I advise you to consider starting to use Kotlin Multiplatform as soon as possible. And that will be it for today. Thank you very much for coming, and as a reminder, network time for Kotlin Multiplatform, JVM, Android, and most Apple targets is available via Maven and SwiftPM today. Please try it out and provide feedback. Thank you.
Thank you, Jorge. Thank you so much. Another round of applause. Great.